that we will be able to so that we can be able to understand it properly. So this is going to be the second series, because the other one we called it series 1. So we are going to call this one the series 2. There are a few things I've told you I'm going to skip, and under some pages I'll be informing you which page we are skipping, and then we shall be able to come back and cover them afterwards because of the arrangement in the handout. So specifically, when you look at page 30, is it 38? We are supposed to go to what we call the convergence of series, and that's where I think we stopped last time. So this is the definition. When you go to this, then this is, we are going to call this one a series. This is the 2. And then when you look at properly, what we have to look at, it is a definition. We are supposed to pick on from definition. This is the 3.48. Can you please go and then check? That is page 38. Can you go and check that page? And we are saying an infinite. And we said the last time that whenever we say infinite series, someone can just simply say series. So meaning that you should be aware of what we are talking about. And we said last time that when we talk about an infinite series, we are referring to something of this kind. This is maybe n is equal to 1 to infinity. Of this is an. That's what we are referring to as being finite. And we said for simplicity of time and for other things, maybe time and space, we can just write something of this nature. This is an. So if we just write something of this nature, then it implies that we are referring to an infinite series. Now we are moving away from the other series of high school we covered, where we just say, okay, we are having a series which is finite. So here we are saying, if we have a series which is maybe AK, this series is said to converge. This series is said to converge, maybe to S. If I follow the definition in the handout, it converges to S. And we said if so happens, if this series here, it converges to S if, meaning that we are now defining if it's having a partial sum. And remember, a partial sum, it is what we say the other series of high school, that we take part of those series, which is most cases we write it as Sn converges to S. And when we say that converges to S, simple that we should take as n goes to positive infinity, then we look at the limit of Sn. And if this is true, it goes to S, because remember from the other side of sequences, we said if you're having something that is maybe Sn converges to S, then this implies that we are going to take a limit as n goes to infinity, and we specifically may say positive infinity. Of this is the same thing, that this one should equal to S. What does it mean? If we can get the partial sum of a given series, and we find that it goes to the sum S, then we conclude that also the other sequence, which is the sum as n goes to infinity, sorry, n from 1 to infinity of n also do what? Do converge to S. That is the interpretation there. That is the meaning of that definition. Now, remember, we said the moment you say it is a series, then you are summing up. That is the interpretation. And then we should know, now since we are talking about convergence, then we should know, when does it diverge? When does it diverge? It implies that if we get a series, okay, if we get a partial sum Sn, and then we find that it doesn't converge to a certain point, maybe S1, meaning that when you take a limit as n goes to infinity of this is the sum Sn, that this thing doesn't equal to a certain value Sn for every Sn being convergent or being finite. If we don't have that value, then in most cases we do conclude that, okay, what we have is divergent. And then we should now go back, and then we should keep ourselves on track with what we looked at last time. And remember what we looked at last time? We said if you're having 1 plus 2 plus 3 plus other terms plus n, this one here equals to n over 2 into n plus 1. When you look at the base, the formulas I was telling you to be knowing, this is one of them. Then we said if you have 1 squared plus 2 squared plus other things up to n squared, this one equals to n over this is 6 into n plus 1 into 2n. This is 2n plus 1. This is, if this is not clear, it is n over 6 into n plus 1. This is 2n plus 1. The reason why I'm not talking about where n is coming from, specifically n must come from n. And then we said also the third one is 1 cubed plus 2 cubed plus up to others up to n cubed. These ones here, it is equal to n squared over 4 into n plus 1. This is squared. So I'm expecting that at least if you were following properly, at least you remember this. But if you don't know how to write them by now, then please try to wake up and do the revision. So with this, we can try to see what convergence imply in this case. If we try to hijack some examples here, and we see what happens. If we are having something close to, maybe if I have a series, which is in our an equals maybe to 1 over this is the to this. If I have something of that nature, and I'm going to use this example more than once, I think for today. So when you look at it properly, I'm going to try to find some little terms from here, and then I try to see what happens really. Before I add on that, let me add here some other things. If you're having a GP, we know that the sum of a GP, the sum of the first n terms of a GP, I told you to read about it. It is a into 1 minus r to power n over this is 1 minus r. And we specifically said, I'm going to be enjoying this, and we specifically said, this is possible if the magnitude of r is less than 1. This implies that your r should be less than 1, and then should not be greater than -1. That's the interpretation. This is a magnitude, meaning that I'm considering from -1 less r less 1. And I'm taking a situation where this is not equal, less or equal to, this is just less. So that is where I'm trying to tell you to know about the thing. And this one here is what we are going to be using mostly. And I'm going to talk about it just today. I'm going to talk about it, but just take it from now that this is now transferred from the high school. It is the sum of the first n terms. And you also add on that the sum of the first n terms of an AP, the sum, if I have if I have AP, the sum of the first n terms is n over 2 into 2a plus this is n minus 1 of d. So this is n over 2. This is the sum of the first n terms of an AP, and much of this I may not discuss it today, or we may not have it written now. So from there, and as you are trying to record those things, as you're trying to record down those things, you should be able to remember them every time you are having a problem on the table. So with this, we can now try to see if I want you to see how do we apply the other formula before we go to testing for convergence. So when you look at properly, this is this here as a series. This one here as a sequence. This is a sequence and not a series. Meaning that I can write this as this is the this is power 2 power n. How do I see if this one here converges? I want to see if it converges or diverges. That is the question. We are testing for convergence or divergence of this. That's what we are targeting. And if that is the case, we can try to see that if we try to expand, remember this is we are testing for convergence, but this is a sequence. So how do I convert this to a sequence? I'm going to convert to a sequence into a series by adding the terms. So if I try to say that this is summing up of an, I'm summing up. Now when I summing up, then this one now it is a series, not a sequence. And I'm substituting in here. When I substitute in the first term, which is 1, I will get a half. And I add, I will get this is a quarter. I'll get this is 1/8. And this one will continue up to infinity. This one, it is now infinite because it will keep continuing up to infinity. Now, when I look at this expression properly, it is increasing with a certain ratio, meaning that if I want to test if this one here, test for convergence, the definition is saying this one here is convergent. This one here is convergent. Please don't forget that this thing here can be also rewritten as n from is equal to 1 up to infinity of this is an. Don't forget. Now I'm testing for convergence, and I'm saying if I'm testing for convergence, the definition is saying you should pick up to any terms. It is telling me pick up to any terms. Then you do what? Then you add them. Then what you do, you take a limit. After taking a limit and check if it exists. If yes, then it converges. Then the sequence or the series, also converges. That is the thing. That is what we are supposed to do. We are going to pick up to the first n terms, then we add them, because adding them implies that we are now having what we call a series, so a sequence. Then after that, we test the existence of the limit. If it does, then we conclude that the first sequence, the first series converges. That is the thing we are supposed to do. Now this is the one we are having. This is the expression we are having, and from this is from sum of this is n equals to this is a half plus a quarter plus this is 1/8 plus other things. Now you will see that we are having r, which is the same as a quarter divided by a half, which is now I think a half. Meaning that when I take this term divided by this term, I get a half, meaning that I have what we call the common relation, which is r. Also, to confirm that it is the same, I can say 1/8 divided by 1/4, so I will get a half, meaning that I have a common relation. Now, since I have a common relation, it implies that my Sn will equal to what? Now, Sn implies that now I'm now on this paper, I've picked the first n terms, then I'm adding them to get Sn. That's what we have called the Sn, the partial sum. It implies that it will be my A into 1 minus R to N over this is 1 minus R. Why am I taking this? It is because I have a GP indirectly. And therefore, my first term is a half. Then my first, this is a 1 minus R. R is a half. And the reason why I'm taking this is that it satisfies the other condition of R less than 1. This is to power n because I'm taking the first n terms. Over this is 1 minus R, which is the same as a half. When you simplify this, it will be a half divided by a half into 1 minus 1 over this is 2 to power n. Hope you can simplify and see. This is a half. This is a half. So this is why I'm having this guy here. Then 1 minus, it is 1 minus. Then because this is 1 to power n, I will remain with a 1. Then I'll have 2 to power n, I will remain with 2 to power n. This is a thing I'm having. And when I try to simplify this guy here, I will get something of this nature, which is so good. I'll get something like this, which is 1 minus 1 over 2 to power n. And when I try to get the LCM, because remember I'm going to take limits, I'll have something close to, I think I can stop even there because it is already simplified. Now this is our Sn equals to 1 minus 1 over 2 to power n. This is the thing I'm having. Now remember, they have said, the definition is saying, when you are having this Sn, this is the partial sum now. They have talked about partial sum. If that is my partial sum, what do? Now I have to check if it has a limit. And we know to have a limit, we know how to check. Checking for the limit, we checked for them, remember. I'm going to have this is the limit as n goes to infinity of this is Sn equal to the limit as n goes to infinity of this is 1 minus 1 over 2n. And then when you check this, remember you covered this. This is taking a limit, then this one will turn like to be 0. 1 minus 0, it will be something like this. So, since limit as n goes to infinity of this is the Sn turns to 1, then the sum, which is An, also tends to 1. That is the we have tested, then we have confirmed that indeed it is convergent, and then it converges to 1. That is the, so meaning that in this case, you can, if someone asks, you can easily say that yes, this one here is convergent to 1. That's what I've shown, and then we are now safe. We have shown it. Maybe here before, maybe if I give you another example before we go to specifics. Yes, I can give you some other example before you go to specifics. Hope I'm not so fast for you to understand. If I take this one to be number 2 and I want to be specific that we are looking at the whatever, we are applying the definition to prove some few things. Just number 2 is that this is the sequence, which is An equals to n squared. Show that the cell this is An diverges. Because the other one was convergent, I want to show you how it diverges, how this guy diverges. So A minute there. I think you have copied the other question well. We want to show how it diverges, and if it diverges, how do we really see that it diverges? So when you look at the cell, from this is from summing up, this is in n is equal to 1 up to infinity of this is a n. This one we shall get. When you substitute in 1, it will be 1 plus, or we can have 1 squared plus this is 2 squared plus this is 3 squared plus other terms there. It will go up to infinity when you try to check properly, if you are so observant. And this is what we want to see. If it diverges, we want to see if it diverges. That's what we want to test. 1, picking or taking Sn. Sn involves picking the first any terms. After picking them, you add them. And this is what we shall have. You see, this one is like we are using this definition, this guy here of we taking Sn equals to this is if I try to see, this is n squared, 1 squared plus 2 squared plus 3 squared plus. Remember, instead of now going up to infinity, we shall go up to any terms. And by definition, I think we agreed upon this. Among other definitions I've just shown you, this is the same as n over 6 into this is n plus 1 into this is 2n, then plus 1. If you check properly. We have said now the difference with the previous work that we had to do a lot of things to get the sum to the sum of the first any terms. Now this one, it is a clear definition. That's why we covered the previous work. Now someone is asking?
Yes, I'm just asking that in the first example, we consider these terms up to infinity, and then in this second one, you're saying we consider up to the nth term.
No, you get me clear. You get me clear. The last one, we didn't consider sum to infinity. Well, you see, if I try to take you back here, you should remember 2 things. 1, if I take the sum, if I have a GP, if I take the sum of the first any terms, I'll write it like this: 1 minus r to n over this is 1 minus r to this is just r. If I take sum to infinity, I'll write it like this, that I'll take the infinite terms. This is equal to, this is a over 1 minus r. So this is the sum to infinity. This is the sum of the first any terms. So last time I used this one here because I wanted to sum up the first any terms. And I gave you this as an exercise to prove by induction. If you want to prove from the analytical view, we can prove where, and we see where it's coming from, where it is coming from. So that is the difference, please. Don't get confused over that. Now, also here, I'm summing up the first any terms. And then remember, after this, hope now we are together. After summing up this is the mother function. This is the mother function, which is the one which is going to infinity. then we are testing whether this one here, which is the finite now, converges. And when you try to take a limit, as n goes to infinity of this is Sn, this will be equal to limit as n goes to infinity of this is n over 6 into n plus 1 into this is 2n plus 1. And when you try to check properly here, what we are going to have, it is the answer will be infinity. Because remember, whenever you put n, it will be changing. Whenever you put n, it will be changing. And therefore, since the limit as n goes to infinity of Sn goes to infinity, then also limit, then the sum, or which is the series, which is n from 1 up to this, the series this will diverge. It will not converge. Now, we have the definition on the table. And the other things we are going to be seeing them as we are continuing. We have the definition on the table. We have seen how we say that it diverges or converges. The first example, it was specific that it was telling us it converges. Then the next thing is to know when it converges, when it diverges, sorry. Now, I want you to go back to the handout where we stopped immediately after the definition. That on that paragraph where it is saying the frequent cause of the confusion in discussing series is that some of you think that whenever you write like this, it already implies two things. This one implies one, it implies that this is a series. You are going on adding things of a sequence or terms of a sequence. But it doesn't confirm that whenever you have this, it guarantee convergence. No. Sometimes, remember we said when you add, you get two things on the table. You get two things on the table. One, it may be convergent, that is, may be finite. Then it may be infinite. The third one, we said even you may fail to get that term. You remember where we branched to and we went for what? For finite and then infinite. So that's where this one here doesn't mean that whenever I write like this, it guarantees convergence. That is what that paragraph is telling you. Remember, if this one is positive, it will keep adding. Then in most cases you get challenges of just concluding. So when you look at remarks on page 38, the remarks on page 38, I'm going to explain you some, then you read some. I think I'm going to bring in examples. That's when we shall be safe. So I'm going to, when we look at remark 1, that one is telling us that the series which do not converge. What we are saying that if you are having a series, and there is an example you are going to see. If you are having a series which is maybe AK, with this series, with the terms of this series positive, i.e., they keep on increasing. Why are we saying keep on increasing? Because if you are having maybe a series, maybe a sequence which is the same as maybe 1, when you have a 1, you see that when you take a series which is AN, it will be 1 plus 1 plus 1 plus 1 plus 1 plus 1. It will go up to infinity. Meaning at this one, at any time, it will keep increasing, but in most cases, it will increase at a slow rate, but it will keep increasing. And in this case, it will diverge. When does it converge if it is a constant series? It converges when this is AN is equal to 0. That's what they are telling you in that sequence. That if it is equal to 0, it implies that when you take AN then it will be 0 plus 0 plus 0 plus 0 plus up to infinity. So nothing will change, and therefore it will confirm to you that when you take a limit as n goes to infinity of the first n terms, it will give you back a 0, and then you conclude that it converges. That is the interpretation there, and you'll be safe with that. So I want you to go to remark 4. Remark 4. Remark 4. Because please, I'm not going to move with the arrangement of the notes of the handout because of some logical arrangements. Some we are not supposed to be there at first, then meaning that rearrangement is going to be done. So when you go to that remark 4, I want you to look at remark 4. Now, I want you to, after remark 4, I'm going to bring back the other, that number, our number 1, because it will be clear if we use it. Or even you can apply number 2, but we already have taken number 1. Now, when you try to check properly, when you try to see this expression properly, it is telling you that when you take this is the sum of this is an, it will be the same as 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16 plus other terms. Now you see, they are telling you that when you drop some terms, it will not change the meaning so long as you follow a certain order. That's what they are telling you. And they are saying, if you drop this and then you go with these other things, still if it converges, it will converge, but it may be to a point, to a defined point. So that is what they are telling you. And even if you drop also this, but you continue with these other terms, still you may not get the same answer as the answer this one is getting if you have not dropped, but still it will converge to a certain point. That's what they are telling you. So dropping some terms is not a problem, and we are going to see how. Because sometimes the reason why we are having that remark, sometimes I may give you something, or we may be discussing something funny, where you are saying maybe I'm adding an from n is equal to 0, maybe to infinity, and then you realize that your n, that the way you know how to solve doesn't involve n is equal to 0, but what you know that this guy here will be bigger than when you take the sum n is equal to 1 up to infinity of this is an. What have I done? I've dropped 1 from this one here. I've dropped n is equal to 0. I've dropped n is equal to 0. That's why I'm saying that this one will be bigger than this. And then sometimes we say O equal to. And the moment you say O equal to, it implies that you are eligible. You can use this, you can drop this and use this to prove for convergence. For instance, we can have something like this. Let's use the second example. We prove that this guy here from n is equal to 0 to infinity of this is R is divergent. Let's use this, and let's use the simpler one. You can write this question here as number 3. And I want you to refer to that remark number 4. So when you look at this and we try to solve this guy, you remember our n, the sequence we are used to, sorry, the series we are used to, we pick n from n. But here they are moving an extra mile to confuse you. So what you do, we can select, because this one we are not well conversant with, we can just say, okay, this is this is in this is summing up of n is equal to 0 up to infinity of AR. Sorry, AN. This is N. This is N, not R. Because we said these two should tally. This one here will be greater or equal to when I take the sum n from 1 up to infinity of this is n. Remember, this n here, it can be written as n equals to, now this is n. So what am I now doing? It implies that if it is greater or equal to, therefore, I can go with this. I can say, but my sum, this is n is equal to 1 up to infinity of n will equal to. Now I'm going with this part here because this is the cell we are used to where n comes from n. Where it is starting from 1 not 0. So that's where another trick can be. And in this case, we shall have something as good as this is. When I substitute, I will get 1 plus 2 plus 3 plus other terms up to infinity, because I will keep adding. Now, when I take the sum, because this is now the cell. Now I'm going to take the sum of the first n terms, and this one here will be 1 plus 2 plus 3 plus up to plus n. I've picked some n terms. And after picking some n terms, what I'm going to do, I'm going to use the other formula of, remember formula number 1? This is the same as n over 2 into n plus 1. This is the sum. Remember the other what? The other expression I gave you, which is this. I think this is the one, yeah. This is the one. This is 1 plus 2 plus 3 up to n. It will be n over 2 into n plus 1. Just like that. And the previous day we have used this, meaning that when it is a cube, you better use that. Now, remember we said immediately after getting the sum, what do we do next? The moment you get the sum, immediately what you do, you take the limit. And then this is the limit. We can just say taking the limit as n goes to infinity, we have limit as n goes to infinity of Sn is equal to the limit as n goes to infinity of this is n over 2 into n plus 1, and this is infinity. So this implies that our sum n from 0 to infinity. Now this, I'm picking up this guy here. I'm picking up this guy. This is n is greater or equal to infinity. So it diverges. It's greater or equal to the other guy, which is the sum n from 1 to this is infinity of n, of which this one diverges. This one here diverges. It implies that also this guy should diverge. We are going to see even a comparison test. It will work for you better here. So that is that remark there. And I want you to go to theorem 3. Please, I want you to go back and during your free time, I want you to read through theorem 2. Sorry, remark 2. Is it remark? It is remark 2 and remark 3. I want you to read through those remarks. And I want you to go now to theorem. You want the working again? The working has been like this. Then we have concluded like this. So those of you who have finished, go to theorem 3.49. Theorem 3.49. Those of you who have finished, read through that theorem, then we try to see what next. So please go to theorem 3.49. That's where I want to see now, where I want to put some energy now, and then we shall be good in understanding. So theorem 3, please, I've said you go to those remarks, which is remark 1, remark 2, remark 3. You try to read. I'm going to first review them afterwards. I'll come back to them, but not now. So don't get puzzled over them. You read through, you try to understand, you try to see how you can apply them. That is the best thing you can do ever. Now, this is theorem 3.49. And when you look at it properly, it is telling us, if you have a cell which is this, AK, it converges. If it converges, then that sequence must converge to 0. Now, look here. Remember, this is when you add, we have called it a series. When you only pick what you have added, what you have been adding, the terms you have been adding, then this one now converges to, this one here is said to be a sequence. Now, I want you to be able to differentiate between those things. Because when you look at it properly, it is telling us something funny. And when you look at it properly from example number 1, we said that we are having this is we are taking the sum of this is an equals to the sum which was 1 over this is 2n. This it was sum 1 over 2 to power n. And when you look at it critically, when you look at this expression critically, it told us, we showed that it converges. Now we want to see really, does it converge? Does this expression here of the sequence, does it go to, does this one converge to 0? And if we check, it implies that we are going to check that is it true that the limit as n goes to infinity of the sequence, which is the same as an. Now here we don't go with the summation thing. Sum is dropped. But what you do, you pick up only this expression you have been adding, only that. And this expression I've been adding, it is what we call the sequence. So we are taking the limit. Tom. Yes, Tom. Please, sorry for that, but someone has been knocking. So this is 1/2 to n. And you clearly know, let me change the mark. What I'm saying, what I was writing is something good and funny. I've said the limit as n goes to infinity of this is an, and I've said now you drop the sum sign. That's what I've said here, that you drop this sum sign, and when the moment you drop the sum sign, then it implies that you have remained with a sequence only, and then this one here will be limit as n goes to infinity of this is 1/2 n. So we have to ask ourselves, when you substitute as many as you can, you see that the values, when you try to check from the other side of sequence, when you check 1, then you'll be putting a half or 0.5. And this one we did it. When you put it 2, it will be 0.25. And then you see that this guy will keep decreasing, and we shall meet at a certain point called 0. But most of the values will be around here. And therefore, it is enough for us to conclude that limit as n goes to infinity of this is 1/2 power n, it goes to 0 or equals to 0. That is the interpretation. Therefore, since our sum n converged, and already we have seen, then limit goes to 0. So the theorem 3.49 is true. This is when you have used just some examples. So I want you to think about the proof. But with examples you have already seen, this is what they want you to do. We have already seen that if really I have some sequence which converges, then, sorry, if I have a cell which converges, then the sequence converges to 0. That's what the theorem is telling you, and that is all. I want you to think about the proof, then we try to move on. But probably I want you to try it. You try it during your discussions, but don't fail to try it. Now, I want you to note something important here. Something important here. If I have, we have said if I have a cell an convergent, we have said then this one here converges to 0. This is what we have said. I have not said that when the cell goes to 0, I have not said that then the sequence an converges. The contrapositive is not right. The contrapositive is not correct. So when you don't switch this guy, you don't change so that you start from 0, then you go to convergence of the sequence. No, it will be right. It will be wrong. So you should be knowing what you are doing. You should be knowing what you are doing. That is the space. The greatest consequence of this theorem is the contrapositive. After the theorem, after stating, when you check after the space of that theorem, that is what they are telling you. That you don't say, okay, since also this one goes to 0, also this one must converge. Then it implies that you have taken the contrapositive of the theorem, and therefore your work is not right. But it is telling us that if the cell converges, then the sequence converges to 0. But doesn't mean that if you're having a sequence that converges to 0, then that theorem or that cell should equal to 0. Please, I know I'm using these two things, but they are confusing you. But let me make them more clear still. When I say it is a sequence, it implies that you are having only terms. Like if I can have a 1, I can have a half, I can have a third, I can have a quarter, I can have 1/5, and other terms. This is a sequence. Then when do I change this name? All this, and this one here is the same as just writing 1 over 2. So 1 over n as a sequence. Now, when do I change this from the word sequence to a series? I think you must have seen. We said that the moment you say, now I have a series, then it implies that you are adding these terms 1 plus 2, sorry, 1 plus a half, plus a third, plus a quarter, plus 1 over 5, plus other terms. That is the difference only. And a series, it implies that I'm adding up to infinity. The moment you add up to infinity, then the name is called a series. Then if you are having only those terms listed, then we call it a sequence. Then the partial sums, what do we call a partial sum? A partial sum is a part of this series. It is what you covered at high school, and you were nicknaming them as series. The first term, the moment you say nth term, up to the nth term, those are called the partial sums of a sequence. So don't get confused over that. And I'm requesting you to be knowing this small gap here. If you don't know, you are not going to understand anything, meaning that you'll be hearing your Muzungu talking. So you should be knowing what is it. When someone is saying a sequence, what does it mean? When someone is saying a series, what does it mean? When someone is saying, actually saying a series is the same as saying infinite series. So this is something confusing, and therefore you should be knowing. You should be knowing. You know you are bright people, so I am sure you do it. You'll be able to remember. So hope now you are not getting confused with the Muzungu talking about sequence, about series. So I'm sure you are bright. You are great then. I'm going to do something. I'm going to do some special examples here. Then we go down to the work for today. Then we finish. What we have been doing is just introducing one another. And I'm lucky now that I've introduced something. Now, I want you to look at examples 3.50. 3.50, go to that work, please. Go to that work, please. Now, I want you to, I don't know, do I need to calculate number 1? Please check proper and then you answer me.
Yes, sir.
Okay. You see, we have a series, which is this. This is I think we said that even if you don't add on the other things, but if you are interested in them, you can add. And this is 0.0001. So what we are saying is that is this one, we want to show that this one do not converge. And the moment you say do not converge, then it diverges. That is the interpretation there, and we agreed upon that. Now, remember, you go to remark what? Remark 4. That's what I'm going to use. Sorry, it is remark 1. It is remark 1, where we said if you're having a constant, then you are sure that it will diverge, because every time will be adding, and then meaning that you will not be able to get to the value. Please, can you check? I've said go to remark 1 and then you read it again. That remark 1, it is where I wrote for you 1 is here. Let me see if I can still remember. If I can get the paper where we wrote. I think I switched to the papers and I'm not seeing it here. Maybe. I'm giving you time, please, to read through that remark 1. Again. This is what happens now. I'm not seeing that paper again. This is what happens. That this is my sequence here. So this is my set here. K is equal to 1 up to infinity. Of this is 0.001 and this is 0 point. Because this one I don't have where to substitute k, it will remain 0.001 plus 0.0001 plus 0.0001 plus, and this one will go up to infinity. You see that thing? Now I'm checking if it converges or if it doesn't. So I'm picking Sn, Sk, not n, because this one moves with k. So I'm picking Sk. So this one will be 0.0001 plus 0.0001 plus other terms plus up to k. And when you try to check, this one here, if I try to take a limit, as k goes to infinity of Sk, this one will equal to the same limit as k goes to infinity of this is 0.0002 plus k. Because why am I saying 2? Because you see, if I add with this one, normally this plus k, I'll find something better there. Or else, you are free to, if I wait to write this, now it will take you to the other, this one will equal to n ok over 2 into k plus, is it k plus 1? But remember, this one here tally for 1 plus 2 plus, oh, this one, no, this is not changing, sorry. I was right, but I changed this. Okay, this is Sk equals, this is 0.00. The camera is not okay. 0. This is 0.2 plus other terms plus up to k. Because I'm taking a situation where I've added already this. I'm taking a situation where I've added already this. I'm getting this. I maintain this. I get this. Now, I'm going to take the limit. Taking the limit, Sk will equal to infinity. Because when you take the limit, it implies that if you put k is equal to infinity, you get infinity answer. Because the infinity plus any other value still will get infinity. That is the thing. And when you try to see that properly, then it diverges. Meaning that since the limit as k goes to infinity of Sn does not exist, It diverges. SK. Sorry. Then also the other cell, which is the k is equal to 1 up to infinity, of this is the 0.0001, will diverge. Actually, it will not will, but it diverges, because we are sure now, we have proved it. And then number, I'm going to leave out number 2 for you to try it during a few times, but it's not an exercise. But I want to try summing up k is equal to 1 of this negative 1 up to k. Up to k. I want to show that this one diverges. I want to show that this one here diverges. That is my target. And how do we show this? We are going to expand this guy. This is the k is equal to 1 of infinity, negative 1 to k. This one will equal to, I'll get, when I put 1, I'll get negative 1 plus 1 plus negative 1 plus 1 plus negative 1 plus 1 plus other terms. You will see that this one here will equal to, it will be a 0 whenever I put n odd. It will be 1 whenever I put n even. Because remember, this is when it is 1, this when it is 2, this is 3, this is 4, this is 5, this is 6, and others. So, look at this properly. You see that when I put 1 which is odd, it is giving me 0. Is it? It is, when I add this and this, it will be 0 when I reach even. No, it will be negative 1 here, not 0. And when I put odd, it will be negative 1. Because when I put 1, it will be odd, so negative 1. When I put 2, it will be even, so when I add, it will be 0. It will be 0. So I think I'm clear now. When I put 1, it will be negative 1. When I put 2 even, it will be 0. When I put 3 odd, it will be negative 1. When I put 4, this kills this kills this. It will be 0. So taking limit. So taking Sn, we have still Sn equals to, it will not change, it will be negative 1 when n is odd, it will be 0, n is even. When you try to check properly, it will not change anything. Because whenever, here I'm adding up to infinity. Now my Sn, it will be just negative 1 plus 1, negative 1 plus 1 plus up to plus n. It implies that to me, it will remain this. Actually, the best way to do this is to start with this, you stop there. Because it will go up to infinity, you may not write this, but you may just say, I'm picking up this, then you reach there. I think I should reorganize it. But it is okay, it is okay. So, I've said when you take the sums, it will be negative 1, 1, negative 1, 1. Meaning that when you put odd numbers, it will give you negative 1. When you put even numbers, because you are summing up, it will give you 0. Don't forget, you are summing up. So taking sum n, meaning that when I take up to only any terms, I'll have up to any terms here. Then still it will come back in the same way. And then when I take a limit, so limit as n goes to infinity of Sn does not exist. Why am I saying that it doesn't exist? You will see that when I take a limit, I will get these two answers. And we said the limit must be unique. We said the limit must be unique, should be one value. But when you see, these are two values. So we cannot converge. These two limits cannot converge to one. Meaning that every time you'll be having vibrating answers, vibrating answers, vibrating answers. And then finally, this guy here, we shall not have the answer. Since this one, the limit does not exist or diverges to infinity, then also this one here, which is k is equal to -1 to infinity, of this is -1 of k, this one here will diverge. So you see, that is the thing. But the trick is here. The trick is to know this guy here, how it will vibrate. How it will vibrate. That's where the trick is. And sometimes they can give you something like this. So you should be knowing how these things vibrate. K is equal to 1 up to infinity. Of this is -1 to power k plus 1. If this is still a question, what do? You will see that when you try to expand, it will be giving you, this is in the first one will be 1, the next one will be -1. The next one will be 1, the next one will be -1, up to infinity. When you pick Sn, it will be 1 minus 1 plus 1 minus 1 plus up to n. It will still give you the same answer. Now you look here, please. Look here. This is an example. Also, you look
so the
here.
camera is not clear.
The camera is not clear. Maybe the network. But can you see something now?
No.
You cannot see. Let me change the page, maybe. What I was saying, that in a case maybe, I was telling you to know that some few things here and there, they do change the vibrations. And I was telling you that maybe you can have something funny like this. This that you are summing up from k is equal to 1 up to infinity of -1 of this is k plus 1. Hope now you can see.
Yes.
Okay. And I was saying, this guy here, when you substitute 1 here, it will be 2. So I'll get 1 minus 1 plus 1 minus 1 plus other terms. And this one will go up to infinity. Now, if this is true, you will see that when I pick my Sn, it will be 1 minus 1 plus 1 minus 1 plus other terms up to n. It will do the same. You will see that when I've put odd number, I've managed to get a 1 when n is odd. And it is now 0 when n is even. You will see here that when n is equal to 1, these are sums. When n is equal to 1, which is odd, I have a 1. When I go to n is equal to 2, I'm going to substitute here, I'll get -1. And because I'm adding them, this one here will go back to 0. I'll get a 0. When I go to n is equal to 3, which is odd, I'll go back to 1. Then when I go to even, this one also will kill this. So 0 plus 0, I'll get a 0. Like that, I will continue up to n. Meaning that my n here will be odd, then I get a 1. It will be even, I get a 0. And then, since Sn, you want k. If you want k, it is okay, but remember, I've just picked up to any terms, meaning that you are free to take k or n. Okay. I think now you are safe. If you want k. Now this is, if I take my sk, now this one here will not exist or doesn't exist. Does not exist. Why it doesn't exist? It is because of this funny bit of it, that it is giving me two divergent answers whenever I put different k's. If it is giving me two different answers, then what does it mean? It means that it diverges, or the limit does not exist. And therefore, also this guy here, which is k is equal to 1 up to infinity of -1 of this is k plus 1, and then in this one I conclude that it diverges. Now the difference with this is 1. You see, this is the guy I had at first. If I bend on this paper here, this is the guy I had at first. This is the one. This is the guy I'm having second. So you should be knowing when to do what. When you try to see, this is the guy I had first. This is the guy I had second. But still, the vibrations will see that they are similar. They are not the same, but they are similar. So you should be knowing what you are doing at any time t. And that is the thing there. And I want you to go to number 2. After number 2, we go to specifics and determine how to determine convergence, because we have seen what it means to be convergent, but we don't know the methods of convergence. Now, let's go to number 2, please. And this one is going to shock a bit. We want to show that this sequence here, 1 over k, which we call harmonic series. We want to show that this sequence, this series here, this one here, that it diverges, which is the read it through number 2. Let me read it through question number 2, then we try to see how we can move. So let's try to. I know Mugisha, okay? I've said we on number 2. And we are saying we want to show that this guy here, which is the k is equal to 1 up to infinity, 1 over k diverges. This is the question now on the table. And if you want to show that kind of divergence, we have to go back and then we see what next. And here I'm going to generally deviate a little bit from the knowledge we have now in the head. Now we are going to let summing up of this is 1 over k equals to when we substitute, we shall get 1 plus this is a half plus a third plus a quarter plus 1 over 5 plus 1 over 7 plus 1 over 6 plus 1 over 8 plus other terms. Hope now the camera is okay, the way we were complaining about. And then look here, please. I'm going to say this guy is greater or equal to. Look here, please. Remember, this one is a 1. If this is a 1 and I reduce this guy to a half, it implies that what will be on this side will be bigger. Because remember, this is a 1. I have a 1 here, but I've reduced 1 from 1 to a half, meaning that now what I will have is smaller. And therefore, plus this a half here, this one here. So I'm going to close this into the first bracket, plus. Now, I want to reduce this guy, this. Actually, I want to reduce these two. I want to reduce these two here into a quarter. If I want to reduce this guy into a quarter, then it implies that I'm reducing a third to a quarter. And therefore, I'll have this is a quarter plus a quarter. And still, it will be telling me the same, that the answer I will have this side will be bigger, meaning that this thing here will be bigger than the one so far generated. Another thing, I want to reduce from here into 1 over 8, meaning that I'm going to have 1 over 8. I'm reducing this one to 1 over 8, 1 over 8. This one here, 1 over 8. This one here, 1 over 8. Then plus other terms. Why am I doing this? I'm doing it because of one reason. I want each expression to be in terms of a multiple of 2. I want each of these terms to be a multiple of 2, so that I can be clear with what I'm doing. So each term is in a multiple of what? Is in a multiple of 2. That is what I want. And therefore, because this guy, you see, this one here, you see, the whole of this expression here is equal to. That's why I'm changing from greater sign or equal to equal. I'm referring to what I've just written. But what I've just written, this one, it will be less than the one which is there. Please, I've said, what am I doing here? I've reduced from 1 to a half. Remember, 1 is bigger than a half. 1 is bigger than a half. If 1 is bigger than a half, this is 1 bigger than 0.5. It implies that what I will have here, what I have here, is therefore bigger than what I'm writing now. That's why I'm using this. And I'm taking this a half, I'm maintaining this. Now, the next multiple of 2 is a quarter. So I have to write this a third in terms of this. That's what I'm doing. So I'm writing this in terms of this. And therefore, it implies that because a third is bigger than a quarter, it still confirms to me that I'm still maintaining the greater sign. And I'm having this up to there. The next multiple of 2, or a square of 2, it will be 1 over 8. So from here to there, I'm writing them in terms of 1 over 8. That's what I'm doing. I'm skipping 1 over 6. I'm not writing this in terms of 1 over 6 because of some reason. That it is, I want to 2 power n. If it is to 2 power n, a 6 will be skipped. That's why I'm also skipping it. And in this case, I will have this is equivalent to, actually this one may not be power multiples, but it will be powers of 2. 2 to power n, that's what I'm writing, 2 to power n. I want each expression to 2 to power n. I'm rewriting this. Therefore, I'm not writing this again, but I'm writing equal, because this equal sign equals to what I'm writing here. I'm not changing anything here. I'm rewriting it. That's why I'm changing from here to there. But here, what I will have here, it will be still greater than, it will be less than this, the first expression. So there, I'm going to have this is a half, then plus this is a half. Then I want each expression, then plus this is 2 multiplied with a half, with the quarter, because remember this is a half, is this a half? Hajat, okay. So you see, this one and this, it is a half. This one with this, it is a half. Then I'm on this, there are 2, so that's why I'm saying 2 times a quarter. Then plus, when you try to check out properly, these are how many? 1, 2, 3, 4. So there are 4, but each is 1/8 plus other terms. So this is equivalent to this is a half plus 1/2 . Then plus this is a half plus a half plus other terms. And this is the sum. This implies that the sum of this is 1/k, which is this guy, is greater because of this sign, is greater or equal to a half plus a half plus a half plus a half plus other terms. You will see these are constant terms, so it diverges. This is by remark 1. We are going to use another method to solve this, because I'm seeing many people asking me questions here. But that is the expression. I'm going to upload for you the video. You look at it again and again. You'll be able to follow. But what you should know, this is how you do it. But we are going to see another method, which is other methods. Even it's not 1, but there are like 4, which can solve this. So I know this one here doesn't have a basis for it to present. But what you should know, we are writing this expression in terms of constants. And these constants, which are not increasing. So we are changing from here to these ones which are increasing to the ones which are standing still or which are stable, which are constant values every time. And if you're having a half plus a half plus a half plus a half, it is calling for example number 1, this guy, where we had summing up of 0.0001. It implies that k is equal to 1 up to infinity. Remember we said this guy will continuously be this value. And then we said since it is continuously constant, then it will diverge. So we have managed to write this expression in terms of halves. And if you have managed to write it in terms of halves, meaning that these values are continuously, these values half plus a half plus a half plus a half plus a half. And by lemma 1, because I've said if you can write it in terms of halves, then it will diverge. And the divergence, that's why we wrote goes to infinity, because it implied divergence. It implies divergence. So, I want you to skip from page 39 We have finished page 39. You skip page 30. You skip page 40. You go to page 41. Then we talk about tests of convergence. This is 3.7. I want you to go there. And we shall, next time, I think we shall have this order. We shall start with the infinite sums as tests of convergence as the methods. We shall have geometric terms, sorry, geometric sums. We shall have the P-series test. These are tests. Geometric sum tests, infinite sum tests. Then we shall have comparison test, and then we shall have limit of comparison test. In that order. Then maybe we shall add a ratio test. Then we shall have absolute, with the one we have skipped. The one which is on page now, what? So these are the ones we shall have in the next lecture. And therefore, I think we can, today I think we can pause up to there, reason being, we have covered, I think, too much work for today. And in this case, I think